Good afternoon, faculty, staff, students, alumni, and distinguished guests. Thank you for being here this afternoon to celebrate the establishment of the Hasso Plattner Endowed Chair in Artificial Intelligence at UC Irvine. I'm Marios Papaefthimiou, Dean of the Donald Brent School of Information and Computer Sciences. It's my honor to welcome SAP leadership who have flown in from all over Germany, Seattle, Silicon Valley, or have braved the LA traffic to be here. Also, many of our friends from the SAP offices in Newport Beach have zipped to our campus, a quick 15-minute drive to get here. Thank you for joining us. It is great to see such a strong presence from literally across the globe. I would also like to welcome our ICS and UCI community, including campus leadership, associate deans and department chairs from ICS, Professor Smyth's family, over Zoom, members of the ICS Leadership Council and members of the ICS Industry Advisory Board from all over the country. And last but not least, I want to acknowledge the faculty, staff, and students and alumni from ICS and across campus. Shortly, we will hear from Professor Padhraic Smyth, the Inaugural Hasso Plattner Endowed Chair in Artificial Intelligence, about the past, present, and future of AI and how he has helped shape the field through his contributions. But first, I'd like to share a few thoughts, so bear with me. I had the privilege of meeting Hasso Plattner in person in September 2019 during the grand opening of SAP's offices in Newport Beach. A striking statement he made during his public remarks was that one of the reasons that SAP opened its office in Newport Beach was proximity to the UC Irvine campus and the excellent research program in artificial intelligence. This was certainly gratifying to hear and a great way to start our school's partnership with SAP, initially around research on natural language processing, electronic medical records. Over time, it included projects recruiting, professional master's programs, so on and so forth. Little did I know that 6 years later, the partnership would blossom to include the establishment of an endowed chair in ICS named after SAP's co-founder. Hasso Plattner has established SAP as one of the leading technology companies in the world and the most valuable company in Europe, a remarkable achievement. He embodies many of the characteristics we strive to instill in our students in ICS, a spirit of entrepreneurship and a determination to succeed through vision, passion, and hard work. Having this endowed chair in our school is not only an honor, but it's also an inspiration for our students, something we're particularly grateful for. SAP and ICS are strategic partners in the true and full sense of the term. The underpinnings of our multifaceted relationship are mutual success and close engagement, encompassing advanced research projects at the PhD level, real-world projects for professional masters and undergraduate students, active recruiting amongst most of our graduate and undergraduate programs. The establishment of this endowed chair propels our partnership to a new level, setting a foundation for what I would like to call the SAP-ICS Alliance. Through this alliance, SAP creates a new blueprint for industry-academia partnerships, building them around a portfolio of short, medium, and long-term objectives. Given the importance of industry-academic partnerships, particularly in the rapidly growing area of computing, I very much hope that the high-tech industry follows SAP's lead. I'm grateful to our friends and partners at SAP for leading the way and for their generosity towards and trust in our school. Now a few words about Padhraic and this election. When I asked the Distinctions Committee in ICS to select among the many nominees a small handful of the most fitting candidates for the chair, they countered, echoing Hasso Plattner's own words at the opening of the SAP office in Newport, that this was mission impossible, given the many outstanding AI researchers in ICS. What would be the attributes of the ideal candidates, they asked. How would you describe them? The usual list of attributes that we academics love to give includes outstanding research, excellent teaching, far-ranging service. And while that's correct, some combination of achievement of these things is expected at a minimum from an endowed chair. So what would make them stand out from the rest is the question. Well, to borrow a phrase that I believe originated in American football, okay, and is now used across sports and musical theater, what we were looking for is a so-called triple threat. Okay? For a performer, this means they excel in singing, acting, and dancing, and can seamlessly transition between the three. Put simply, there are no weak spots. For us in ICS, I can call this person a flag bearer, somebody who exemplifies our school's excellence in AI across the board in every possible way, whether it's research, teaching, or service, somebody whose work has made a positive impact both on the research community and in industry, and whose students attest to and continue that person's legacy. As I'm sure you will conclude from this lecture, Professor Smyth fits this description perfectly. Padhraic Smyth is Distinguished Professor in the Department of Computer Science at UC Irvine, with joint appointments in the Departments of Statistics and the School of Education. He is an ACM Fellow, IEEE Fellow, AAAI Fellow, and AAAS Fellow. Padhraic's research in machine learning, probabilistic modeling, and data science has set the foundation for transformative advances across diverse fields such as climate science, medicine, and education. His work continues to influence both academic researchers and industry practitioners globally, validating his exceptional leadership and enduring impact on the field. His early seminal work in decision tree algorithms, hidden Markov models, and probabilistic graphical models earned accolades with multiple Best Paper awards, including at the renowned ACM SIGK-DD conference. His pioneering work on statistical topic modeling revolutionized text analysis methodology for over a decade and remains integral to fields like digital humanities. In recent years, Padhraic has directed his research towards human-AI collaboration and algorithmic fairness, addressing contemporary challenges in artificial intelligence. Padhraic was the founding director of the UCI Center for Machine Learning and Intelligence Systems from 2007 to 2014, and founding director from 2014 to 2018 of the UCI Data Science Initiative. He has been serving as co-director of the HPI Research Center on Machine Learning and Data Science at UCI since 2020, and as faculty director of the UCI Machine Learning Repository since 2002. His professional service outside UCI includes founding director and executive committee member of the ACM Special Interest Group on Knowledge Discovery and Data Mining. That's the SIGK-DD thing I mentioned before. Program chair for the 15th ACM SIGK-DD conference and associate editor for many flagship read journals in AI and statistics. Padhraic has received research funding from agencies such as NSF, NIH, NASA, NIST, and from industry such as Adobe, eBay, Google, IBM, Qualcomm, and of course, SAP. I should point out that this collaboration with SAP started with the launch of SAP's Innovation Center in Newport Beach in 2018 and focused on automated speech recognition and natural language processing. In addition to academic research, he's active in industry consulting, working with companies such as AT&T, Netflix, Nokia, Oracle, Samsung, Toshiba, and the list goes on and on. Last but not least, Padhraic has supervised more than 30 doctoral students and postdoctoral research associates who have gone on to assume leading positions in academia and industry, including as CTO of a public company and serving as faculty in top computer science departments. One of his students has already been inducted into our ICS Hall of Fame. Such is the scope of your own legacy. I think you will agree that Padhraic is indeed our own triple threat, our flag bearer, and I could think of no one more fitting to serve as our inaugural Hasso Plattner Endowed Chair in Artificial Intelligence. Please join me in welcoming Padhraic.
Thank you, Marius, for the very kind introduction. If you're expecting singing and dancing, I'm sorry to disappoint you. That won't be happening in the next hour at least. It's truly an honor to get this endowed chair, and I'm super grateful to SAP for giving this chair to UC Irvine. I'm also honored that it's named for Hasso Plattner. If you haven't read his bio, it's pretty inspiring, especially if you're European. He got his degrees in the late 60s in Germany, worked for IBM, and then in 1972 did that most un-European thing of a startup. I just can't imagine doing a startup in Europe in the 1970s. So he then turned SAP into a phenomenal company, and then after that has been very involved in philanthropy over the last number of years in the US, in Africa, in various places. So it really is an honor. All right, so let's go ahead. I'm going to chat for the next, we'll see how long, 45 minutes or so. First, a few acknowledgements. I want to acknowledge my PhD students, current and past, and the many other students I've worked with. Students are the lifeblood, and you'll see that in my talk. They really make research work. And especially today, literally today, especially in the US, where student funding is being threatened and so forth, it's very important to acknowledge this, that all of the AI I'm going to talk about, most of that came from students. Faculty played a role, obviously, but students are critically important. Yeah. I've had the opportunity to work with tremendous colleagues in the past and currently at UCI. You don't get to do great research on your own. It's very much a society of researchers. Funding support, again, from National Science Foundation, National Institute of Health. If you imagine that AI was somehow invented at OpenAI a few years ago, that is not true. Hopefully my talk will help convince you of that. A lot of basic work at universities and funded by agencies like NSF over the years. And also funding from Hasso Plattner Institute the last few years for our students, and industry funding from SAP and from Google. We're very grateful for that. I'm going to start with, it's okay to boo at this slide actually, but for reasons people in the US will know. But I'm talking about predictions about AI. So in 2015, this person, whom I won't name, predicted that we would have self-driving cars everywhere in 2 years. Now, this next person, Jeff Hinton, is somebody I admire, but he sometimes gets his predictions wrong, and he predicted that radiologists would be obsolete in 2 years. So this is a slide from last year, but 2024, radiologists are driving to work in their cars still. So the point of this slide is there's a history of AI promising a lot of stuff, and right now we seem to be on the cusp of a lot happening, but do keep in mind that AI researchers have overpromised in the past. When the announcement for this talk went out, it mentioned the title, but then it said in the blurb that I would talk about the future of AI. Well, in mind of the last slide, we don't have a great record of predicting the future in AI, so you're going to hear a lot about the past, a little bit about the present, and I'll say a few things about the future, but not so much. This is also a personal perspective, so it'll be interleaved with my own experiences, and I hope the students here can relate to that. You start out just as a novice, and you too could be up here in a few years getting awards like this. And also, there's no way in whatever time I have left, 40 minutes, to cover all of AI. So if I don't cover your favorite topic or don't name you if you're relatively famous in the room, that's okay. I only have so much time. All right, so we've always been interested in notions of automation, robots, going back to even before Leonardo da Vinci, but this is a picture of his mechanical knight, an amazing construction. You had Leibniz, who was thinking about the laws of thought, and he built essentially the first calculator, another amazing gadget. Karel Čapek in Prague had the first to coin the term robot. So there's been a lot of interest in automation, robots, and so forth over the years. We're going to start in the 1800s, and one of the reasons is we're going to start with George Boole. And I like starting with George Boole because Boolean logic, but also George did much of his work in University College Cork in Ireland, where I'm from. So he published his Laws of Thought book, and this was the first time that people wrote down mathematics essentially for simple reasoning with Boolean logic. Side note, George had a relatively early death. Supposedly, the story goes that he walked 3 miles to the university to give a lecture to the students in heavy rain, came back, got pneumonia, and died. And that's real dedication to students. Sad story, but it does rain a lot in Ireland. So George was originally from England. Maybe he didn't quite expect that much rain. So that was more on the mathematical side. On the neuroscience side, you had people like Cahal and Golgi who won the Nobel Prize for essentially figuring out that the brain, we had all these neurons talking to each other, communicating. This generated a lot of excitement. And then in 1948, there was a landmark paper that in some sense fused these two threads of research, McCulloch and Pitts. This is actually a paper, if you're a student, worth going back and reading. It's amazingly well written, really fundamental stuff. And here's a picture of McCulloch and Pitts, very interesting characters, as a lot of the people are in this story of the history of AI. And this, there was a lot of activity around World War II, people like Turing, von Neumann, Shannon, legendary people in the field, founding theories of computation and so forth, leading up to what I call AI Wave 1. And I'll roughly say in the 40s and 50s when this started. And interesting, when I was putting together the slides for this talk, one of the fun things about giving a talk like this is you get to go back and look at historical artifacts. And I didn't realize there were a number of symposia about AI and related topics, but one of the key ones was held at Caltech, just up the road. So I'm going to try to emphasize how much happened here in Southern California, right around us in the last century with AI. So it was a Hickson symposium. Hickson, it was organized by the biology department. McCulloch was there, von Neumann was there, and they were trying to, move forward with mathematical models of the brain and computation. The reviews afterwards weren't stellar. This was from some psychologists. It says, despite all the grandiose claims, cybernetics has contributed nothing to neurophysiology except the confusion of some neurophysiologists. So he was complaining about von Neumann's talk and said nobody understood a word of what he was saying. So again, if you're a grad student, don't get discouraged. Even von Neumann couldn't convince people that he was on the right track. Now, entering into the picture is somebody who's often referred to as the father of AI, John McCarthy. And McCarthy grew up in Los Angeles, self-educated, taught himself mathematics, went to Caltech, supposedly skipped the first 2 years of mathematics classes at Caltech, which is quite an achievement. Another thing I found out is that he has an Irish connection. His father was from Ireland, born in County Kerry, and had come to the US. His mother was Lithuanian. They moved out to Los Angeles. So again, kind of the way all these sort of ideas came from different places, pretty amazing. Anyway, John was at Caltech as an undergraduate. He was finishing up in 1948, and he attended this Hickson Symposium, and he, at least according to the record, was fascinated by von Neumann's talk, and this idea that you could think of basically of the foundations of AI and some fundamental principles for how we might use computers to simulate what the brain does. So from there, McCarthy graduated. He actually went to Princeton and did some serious math and differential equations because this AI stuff still wasn't a real thing. Got to an appointment at Dartmouth and then proposed to the Rockefeller Foundation for a summer program. This is the original proposal that they wrote with Marvin Minsky and some others. Claude Shannon was involved. This is the type of letter that went out. They held the symposium. This was the Dartmouth Summer Conference, considered the start of AI. It was the first time that the word artificial intelligence was used. There was some debate about the word, the term artificial intelligence. McCarthy came up with it. And a few things to notice, the picture on the left, there's not a lot of diversity here in terms of, and I'd like to think in, 2025 that we've improved a lot in terms of diversity, but I'd say we haven't really done a great job. There's room for improvement. So anyway, we'll leave it at that. On the right are various names. This is Ray Solomonoff, who attended, and his notes, you can find his handwritten notes digitized online. And here's his list of people he remembers attending. So people were coming and going, it lasted a few weeks. You had the likes of McCarthy and Shannon. You also had McCulloch with the McCulloch and Pitts famous paper. John Nash popped in. The story is he wasn't super impressed by these AI people, only stayed 2 days. Arthur Samuels from IBM will show up. Herbert Simon, Alan Newell, who also ended up doing a lot of work. What's interesting here too is that the role, for example, that IBM research played here. There was universities, but also companies. And companies were important. They had the computing power. And at the time, IBM was quite a powerhouse in terms of computer science research. So the Dartmouth Commerce didn't produce sort of any fantastic new sort of theories or ideas. People kind of continued doing the same thing. And in the 1950s, people continued, Newell and Simon started to develop fundamental results in various types of modeling. Arthur Samuel is someone I want to mention for a particular reason, well, a few reasons. He's one of the first people credited with using the term machine learning. So in the 50s, he was originally at the University of Illinois. He went to IBM and later to Stanford. And while he was at IBM, he developed some really amazing ideas for the time that really foreshadowed what we now call reinforcement learning and taught a computer to play against itself, other simulations, and to improve its performance in playing checkers. So in terms of search and learning, a lot of ideas that he was instigated. Now I mentioned Samuel for another reason. In 1962, some of you will know about Martin Gardner, who wrote columns in Scientific American and popularized a lot of ideas in mathematics. And he wrote this article about, built on Samuel's work, but also Donald Mickey's work at the University of Edinburgh, where if you didn't have access to a giant, expensive IBM computer in the late 1950s or early 60s, you could simulate it with matchboxes. I won't go into the details, but it involved getting a bunch of matchboxes and putting buttons in and out as you, played this, simulated this game. One of the reasons I mentioned this is in the 1970s in Ireland, when I was growing up as a teenager, I came across this article. In fact, I have one of the copies of the book here with me. It followed me all the way out here. Martin Gardner's article about learning machines. And I remember distinctly reading this at the kitchen table and then getting a bunch of matchboxes and trying to replicate what he was describing. Unfortunately, even though my dad smoked a lot, I ran out of matchboxes pretty quickly and didn't quite fulfill the learning machine. But I do remember being absolutely fascinated by this idea of machine learning, even though for another 10 years it didn't really come back to me. But it was there. So following on from the likes of Samuel, Frank Rosenblatt was another key figure around 1960, essentially the first person to develop what we would call neural networks, very simple neural networks where you could learn the weights mainly for pattern recognition problems. Interestingly, he actually built these in analog hardware, actual physical devices, rather than simulating them on a digital computer. Another reason he's somewhat, maybe slightly infamous is this is maybe the first example of AI hype. The print's too small for me to read it here, but the Navy revealed the embryo of an electronic computer today that it expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. This is 1959. So, this AI hype, AI has gotten ahead of itself more than once over the years. So, 60s and 70s, what's interesting if you look at the history is that in some sense, things split into, I wouldn't say two camps, but there were two natural groups of people. There was the more symbolic logic, knowledge representation that I show on the top here. And then below that, people more maybe in electrical engineering, doing more pattern recognition and neural networks, focusing on things like speech and vision. The top you might think of as general characteristics of intelligence, very symbolic, more computer science oriented. The bottom a little more practical, trying to solve particular problems of interest. Progress continued. And one interesting thing in the bottom group was this fellow called Jeff Hinton that we saw earlier. He was doing his PhD in Edinburgh in the 70s. And what some of you might not know is that he is the great-great-grandson of George Boole. So there's that connection from Boole all the way to Hinton. That is quite cool, actually. So, all right. So the 1980s saw essentially the second wave of AI, and where there was some major progress. On the symbolic side, there was continued progress in knowledge-based expert systems. Some of you here are old enough to remember the excitement about rule-based expert systems. There was a lot of commercial activity. A conference on machine learning started in 1980. It was at CMU. In 1987, it was held here at the UCI campus. UCI was very heavily involved in machine learning very early on. In fact, the journal Machine Learning's first issue in 1986 was edited by Pat Langley, who was here at UCI at the time as a professor, also had papers by Newell and Simon. And so machine learning was getting going in the early 80s. Meanwhile, back in Ireland, I was doing electrical engineering in the early 80s, and I'm showing you analog to digital converter devices. And the one on the left is the old style, big, expensive piece of equipment. The one on the right is what was happening, if you like, in the 70s and 80s, miniaturization, putting things on transistors. And this absolutely fascinated me as an undergrad student, that you could put, you know, in some little gadget, something that would convert analog signals, sound, whatever, into digital zeros and ones, and the potential for that. I was like, this is so cool. You know, if we can digitize music and speech, we could do a lot of really interesting stuff. I didn't think it would take another 40 years to get there, but I was really excited about this. So I applied to grad school, and I ended very fortunate to end up at Caltech, which turned out, I didn't know it, but turned out to be a hotbed of activity in machine learning and neural networks in the 1980s. I should, a side note, say another reason Caltech has great memories in my mind. I met my darling wife, Krista, there shortly after I got there, so that was also a really good thing for me. In 1985, my advisor came into my office, and I remembered the day. I remember the desk I was sitting at. He put this book down. This was the proceedings of that first conference on machine learning. It was called Machine Learning, a black book with a red thing on the front page. And he said, I don't know what these guys are doing in machine learning, but it seems interesting. And I said, okay, I'll take a look at it. You know, you're a grad student, you do what your advisor asks most of the time. And I started going through it, and I was like hooked for the second time, if you like. Except this time now I was a grad student and access to computers. I didn't need matchboxes and so forth. So I straight away, you know, I said, okay, this machine learning thing I think has promise, and it turned out to be a reasonable decision in the long run. I did my PhD thesis on it, and things worked out quite nicely. One of the people on my committee, and who was very prominent on campus, especially pushing ideas of neural networks, was John Hopfield, who won the Nobel Prize in Physics for his work. Very influential work in neural networks. So you have people like John on campus coming over to electrical engineering, no slides, he'd just get up in front of the board and start writing stuff. Very inspiring. And again, I would encourage grad students, don't assume that the way we've organized things for seminars and departments is the way it will be in the future. Feel free to go to the math department, go to the biology department, go to cognitive science. Some of the most interesting stuff may be happening somewhere else on campus. Also running around were people we know here at UCI. Eric Mjolsnes was a student of John Hopfield, working on neural networks in the mid-80s. Pierre Baldi was running around doing very advanced math on neural networks and so forth. Down the road at UC San Diego, again staying in Southern California, David Remmelhart had a postdoc called Jeff Hinton, we've heard of him before, and Ron Williams, and they published this paper on backpropagation, which if we go back to Rosenblatt didn't really know how to make complicated neural networks and get them to learn from data. And this backpropagation algorithm essentially solved that problem. It's a very sort of nice extension of basic calculus, of computing gradients efficiently, but it was hugely influential. So you had this activity going on in the early 80s, people like Hinton and Hopfield and so forth, and this NeurIPS conference that we're now familiar with, arguably the biggest conference in machine learning, or certainly one of them, was started in the late 1980s. And again, something I didn't realize, that the very first NeurIPS conference was chaired by two of the people that I knew really well, who were on my PhD thesis committee, Yasser Abu Mustafa and Ed Posner, both fantastic mentors for different reasons. This is a note one sent to the other. So they organized the conference up in Denver. They had Carver Mead talking about analog computers from Caltech. They had Cherry Sinowski, who was at Johns Hopkins, but then came to Salk in San Diego. There was a huge number of people, I think at least 100 at this first neural networks meeting. So the idea is it was very small at the time. Even though I wasn't doing neural networks per se, the gravity, I got pulled into this. At Caltech, it was unavoidable. And so I would go along to the neural network conferences in the late 80s, early 90s. Krista came with me, some of these. And you'd rub shoulders literally and chat with people like Joshua Bengio, Jeff Hinton, Jan LeCun, who went on to win the Turing Award. And I didn't realize it at the time, but these guys were absolutely brilliant, given the computing hardware that they had available. So Jan invented convolutional neural networks, essentially an early paper in 1989. Joshua, a little bit later, another NeurIPS paper, where essentially he laid down the foundations of large language models. And just the foresight of these guys, I was in the room, but I can't say I had the same foresight. It's just amazing what they were able to do. But at the time, nobody knew what the future held, where this was going. And in fact, I'm blanking out sort of the second right-hand side of this graph, just showing attendance at conferences in the 80s and mid-80s through 2000. And on the very bottom, you'll see, don't know if I should do this or not, but no. Very bottom line is NeurIPS. It was a very small conference. Even in the mid-80s, mid-90s, only a few hundred people going to it, even though these fundamental things in AI were being invented. The big AI conferences, HCI and IIII, that's the yellow and orange, they had a lot of activity in the mid-80s, but it was hard to scale up these knowledge-based systems. So there was too much hype, and the attendance died off to a more stable level. And then, of course, things continued, and there was, a good decade or two or three there where AI was kind of respected, but no, it wasn't really a lot happening until, a few years ago when things really took off. Now, you might say, if we knew about convolutional neural networks and language models and these things back in the 90s, why didn't things take off? Well, okay, let me explain this graph. This is your Moore's Law graph where we have log scale on the y-axis and everything is coming down dramatically in terms of memory capacity, price, et cetera, computing. But imagine you're in 1993, say. You're still up, kind of quite a ways up on that graph. And also, just for the students, we didn't have the internet. I mean, there was FTP, kind of, and there was other things, but getting a data set meant writing a letter to some person in Yugoslavia and getting back something called a floppy disk or a tape and then figuring out how to get the data. I mean, it was a very different world. So you guys live in a very nice world for doing this kind of research. So the computing capacity, the infrastructure really wasn't there. The ideas were there. A lot of the fundamental ideas in AI or neural networks existed, but we couldn't take advantage of them. There were other important contributions in the 1990s. It wasn't like everybody sat around doing nothing. Up the road at UCLA, Yuta Perl and his grad student at the time, Rena Decter, who's now a valued colleague here at UCI, developed the fundamentals of uncertainty in AI. And it turned out to be very important. We really need to think about probability and uncertainty. Intelligent agents need that. There was connections made with statistics, and many people involved in this, but Leo Breiman at Berkeley, Mike Jordan at Berkeley, laid the foundations that still help us design large neural networks. There's a statistical thinking behind them, a statistical foundation that sometimes gets lost. So moving on, in my own personal journey, after graduation, I went to JPL, and what I noticed at JPL, fantastic place to work, it was very hardware oriented, a lot of engineers, build stuff, send data back. So JPL does all the planetary spacecraft that don't have people on them. So stuff coming back, looking at the skies, blah, blah, blah. But, I started to realize we're piling up all this data. There was a planetary geologist across the hall from me, and he kept bringing in these disks from the Magellan, these new things called CD-ROMs from the Magellan spacecraft, and the pile was growing and growing. And I was talking to the planetary geologists. They couldn't, the old way of doing it was they would print out the images and map out where the volcanoes and craters and everything were. They couldn't. There was hundreds of CD-ROMs. So it was very clear to me that we needed to do something. We need to speed up this whole business of pattern recognition and AI to make progress. So I really wanted to find a picture of the geologists crowded around. I know the picture exists. I just couldn't find it today. But crowded around a big map of Venus, and they're marking it up. And so I asked Google's AI tool, Gemini, to give me find me this image. And it gave me back a historical image of planetary geologists working with the large map of a planet. Well, there's a map of a planet, but if anybody can find the planetary geologists in this picture, let me know at the end of the talk, because I couldn't. So AI is still, still there's a ways to go. Okay, so we got to work on this with the Magellan spacecraft, trying to recognize volcanoes on Venus. We got a lot of publicity and successful paper. And we were doing it in two stages. First building kind of filters or feature extractors, and then a machine learning classifier on top of that. And that was really hard to work with. We didn't make a huge amount of headway. I'll get back to later why that's important. One of the other things we were realizing is that data sets were becoming critical. You really needed lots of data, lots of good quality data, labeled data. David Aha was a PhD student here at UCI in the late 1980s and had this great idea of just putting data publicly available on, well, the FTP site as it was before the web. And this became the UCI machine learning repository, still running today. Some of the grad students might be here that are helping to run it. I see Rachel over there. And yeah, it's a fantastic resource. Became the standard machine learning testbed research and really accelerated research over the years. Another example of this large data, the idea that we needed large public data, was the Netflix prize. In 2006, I got an email saying something about $1 million prize from Netflix. I was a Netflix customer. I was like, why is the spam email showing up? And I was about to delete it when I realized, no, they're serious. They want to run a competition. I flew up to San Jose, talked to the Netflix people. I became an academic advisor. They had a $1 million prize. It was a huge data set, attracted a lot of student interest, including students here at UCI, but it got machine learning researchers really thinking about scale, and the method of stochastic gradient really showed how valuable it was in that. This is a picture of the $1 million being awarded, at least a symbolic check at an event in New York that I went to. It was a lot of fun. Going back to the volcano project, one of the people involved was Pietro Perona, who was then a junior faculty member at Caltech, which is down the road from JPL. And Pietro had this idea that instead of having two feature extraction and then classifiers, you could do it all at once, and you just needed enough data. I remember sitting in his office. He said, we're going to do machine learning for computer vision. And at the time, computer vision was much more model-based and so forth, reasoning about 3D worlds. And I remember listening to Pietro thinking, this is fantasy, this won't happen. But Pietro is a very smart guy, and he had brilliant students like Fei-Fei Li, who went on to Stanford. He had a postdoc called Max Welling, whom we hired here at UCI, spent 10 great years here. And they got this to work. So they started producing large-scale data sets and started challenging the AI machine learning community to build models that could take advantage of them. The one that's really made a big difference is the ImageNet data set. And so Fei-Fei Li developed this, but one of her colleagues working on this is Alex Berg. I don't know if Alex is here. This is a young Alex. In this picture, I didn't find an older Alex. And very important. This had 10 million images crawl on the web. Again, the internet was very important in making this happen. 1,000 class labels. Still a hard problem for computer vision classifier. But this allowed now people to try out really large-scale ideas. And so the stage was set, in some sense, for the third wave, 2010 to now, where deep learning comes to the fore. And what had been happening at the NeurIPS conference was people were continuing to work on neural networks, and we knew about deep networks. And Jeff Hinton, Yoshua Bengio, Jan LeCun, and others continued to write papers. But it was interesting. This graph shows how likely, or well, it shows the fraction of papers that talked about neural networks, basically, in the 1990s at NeurIPS, and it almost went to zero. So the joke among people, submitting papers to NeurIPS was, don't mention neural networks because it might not get in. Neural networks had become this thing that had a lot of promise, but people couldn't scale them up, get them to work. But Hinton and his colleagues really believed. You'd meet Jeff at the conferences, and you'd put, if you were in a corner or something, you'd have to try to get away because he was so passionate about this. And again, I remember this because it tells me that, even if the community is not necessarily supporting your work, if you believe in what you're doing, just do it. I mean, that's the whole idea of research. And it took multiple decades for their vision of neural networks to be realized. So in 2012, the ImageNet dataset was out there. There was an annual conference. Jeff and his students entered the competition, and the graph here shows the improvement that they got. So, there was various competitions going on, and the error rate on the ImageNet classification was high 20s, and in 1 year they dropped it to 16%. And the community went like, whoa, hold on, and they're using deep learning to do this, which people didn't think could work. So they were getting attention. In fact, speech recognition companies had already picked up on this and were using these ideas very early on in speech recognition. So around about that time, people started to realize that machine learning, particularly deep learning, could be used on really hard problems and make progress. By the way, if you recognize Ilya Sutskever on the right, or his name, he became the chief scientific officer at OpenAI and was involved in a lot of that recent brouhaha over OpenAI and so forth. But he was a grant student when this work was done. One of the reasons that now things took off, and they didn't take off earlier, is because we've moved along that curve. You are now here with this, big data sets and much more compute, much more memory. And so there was a convergence, if you like. It wasn't that we had a new theory. The theories existed for the most part, but we had a convergence of data and compute power and so forth. Progress on ImageNet continued, went from 50% up to near 100% today. And 20 or 30 years ago, if you went to an AI conference, you would have the AI part. You'd have machine learning as sort of respected, but not particularly. It's like, well, we let the machine learning people have a little side room over there. They're doing no harm, kind of a fringe activity. And then neural networks, deep learning, would be like one session, Jeff and his students. That's a little of an exaggeration, but AI was very different. Now it's totally different. Deep learning kind of takes over most of machine learning, and machine learning has taken over most of AI. I am not saying that this is a good thing. I'm just saying this is what you will see at conferences and the state of the field right now. I think a balance may be necessary, and some of the ideas of symbolic AI, reasoning, would probably or may play an important role in the future. Let me say just a little bit about what these AI models are. This is a very high-level talk, so just for folks in the audience who might not be super familiar with machine learning. Machine learning, in essence, is a very simple idea. We build this black box, the AI model. It's going to be a neural network, takes in some inputs, produces an output. So the input could be text, images, video, etc. The classical machine learning is the output's pretty simple, like it might be a binary 0 or 1. So is the text in the email, is it spam? Does the MRI contain a tumor? Is the word spoken, the word start, etc. With deep learning, we were able to scale up and get output that was more general. So output that itself is text, output that is image, that's audio. So richer prediction models. Again, the foundations are quite mathematical, but we now can do a lot more applications. So the sort of thing you can do is, for example, take an image of a biopsy, a tissue slide, and then predict cell types, where are the cancer cells in the image. And this is one of the most successful applications of AI machine learning over the years, and now fairly standard and routine. Another area where machine learning is currently making a lot of inroads is in climate data, where you have weather satellite images up to some time, and then you want the output that you want to predict is the future state. We know about text, of course, with ChatGPT, et cetera. What you might not know if you're not in computer science is that these models are actually really good at generating code. You can say, here, write some code to multiply two matrices together. Boom, code pops out. Super helpful. I know SAP is very active in this space, like a lot of other companies. Also interesting, and I think very cool, is you can take somebody else's old code and ask it to summarize it for you. So now input is code, output is text. And just today I saw an article about how Morgan Stanley had used this in the last few months to take millions and millions of lines of old code and help translate it into new code. And what I enjoyed is that the old code was written in COBOL. So how many people here know COBOL or could write in COBOL? Wow, that's cool. All right, really cool. Anyway, so your old COBOL, don't bother going back trying to manually figure out what was written. Have ChatGPT or one of these tools do it. Generative models you've heard about. Really the idea there is that you get a distribution of outputs, samples of outputs, the notion of uncertainty. So I asked Gemini to generate an image of a professor with an endowed chair in AI, and this are two of the samples that it gave me. So I guess I'm wearing a jacket, so that's good. I'm in the right ballpark. But more seriously, this is work we've done with Effie Fafula, Giorgio, and colleagues and students. We can, for example, get uncertainty about rainfall maps. I don't know if Effie is here or not, maybe not, but this has been very cool work. And again, enabled by that black box in the middle. All of these black boxes I've been showing you are somewhat different to each other, but the same underlying concepts in mathematics. So what's inside the black boxes? Well, again, if you're not a computer science or familiar with machine learning, it actually is, it's math. It's a mathematical function, very flexible, nonlinear mathematical function, and it has parameters. They're theta here. There can be billions of these parameters, huge numbers of parameters. Training and learning is just given millions of input and output pairs and adjusting the parameters in a particular way to improve predictions. The details, and students, when they show up in our undergrad class, are very disappointed to hear this, that if you really want to get into this, it's optimization, things like stochastic gradients, statistical loss functions, it's mathematics, it's fundamentals. So, there's no getting away from that. The core here is, it's not some sort of magic stuff, it's fundamental, fitting a function to data, but on a massive scale. A little bit more about what's inside the black box. A lot of them have this sort of notion of embedding that we saw in Yoshua Benjua's work. Goes into an encoder, maybe many layers. There's some notion of a hidden representation and decoding to get the output. The embedding is really important. It takes words, puts them in this vector space, gets away from symbols, turns out to be very useful. The hidden representations, there should be a picture of a cat here coming up, very hard to understand, but very useful. So you're taking the raw pixels and learning this hidden feature space, essentially, that we were trying to design manually in the 90s and 2000s. Now it's being done through learning, but very hard to interpret what's going on. So attendance at these conferences, interest in this area, of course, has grown exponentially. It's hard to get into our own conferences now. Sometimes I'll be going to Europe's or something else and told, oh, we're sold out, and I'll have to call somebody or something. So it's kind of strange, having gone from the early days in Europe's to this new situation. One of the areas, so there's so many areas where AI is being applied. One of my favorite areas is with camera trap data. So with technology, with sensors, you can put cheap cameras out all over the place. They're out here in the mountains, recording mountain lions, etc. And so they're picking up all kinds of behavior of animals without people needing to be around. Here's pictures of panda bears. Now you've got all this data from your cameras. What are you going to do with it? Well, you could employ a team of grad students to go through and annotate. No, you get an AI algorithm. And here it's classifying panda bears and doing a very nice job. And you might or might not be able to see it's coming up also with probabilities. Now, a lot of these probabilities are 1 or close to 1. So it seems to be awfully confident most of the time. We'll come back to that. And you can do this on mushrooms, flowers, insects, other animals. You can do behavior over time, maps. So it's really revolutionized the whole field of modeling animal behavior, as an example. Here's one with shark detections, doing very well. But all these models make mistakes. There's always like a 90-something% accuracy, almost always. And here's the incorrect shark detections. These are ones that we wouldn't make personally. Like a shark on a towel. I guess theoretically it should say it's a shark. A dolphin is not a shark, etc. But what's a little worrying is that the AI model is overconfident. It's very, very confident, high 0.9s on these. And also these are errors that humans wouldn't tend to make. So one of the things we've learned is that AI models behave differently than, say, the human brains, for example, in classifying images. If you want to make these models more accurate, the x-axis here is on a log scale. Typically, you need, the theory tells us and practice that we need orders of magnitude more data to get the error rate down. So if I want to go from 5% to 2%, I don't just need a linear increase, usually need orders of magnitude. And so you have to ask for different applications, when is a 2% error rate tolerable, economical to live with that? So if you're a Google or an Amazon or an OpenAI, you can show billions of dollars at recognizing cats or speech or whatever. But if you're developing something for medical diagnosis or a scientist, you may not have the budget to really build these models. And in medicine, there's a lot of pushing AI into medicine. I was in this room about 6 months ago talking to a lot of medical folks about this. And they've taken seriously the reliability of AI models. And they've noticed, for example, that these models are very good at picking up shortcuts, making predictions on things that shouldn't really, that are non-causal, if you like. So I'll give you one example. This was some work on detecting collapsed lungs from X-ray images. It's a big problem, a lot of time and effort spent doing this. In the original paper, it worked extremely well, but people went back in a later paper and found that some of the success of the classifier was picking up in the data the tubes for people who had a collapsed lung. So in other words, it knew the answer already. So this is sort of data pollution, and again, I'm saying this as a sort of a cautionary note. We get a little carried away sometimes, and it pays to go back and really look at the details, and this was a classic example of that being done. So there was a nice article in the New York Times last week about, radiologists have not gone away, despite, and Jeff Hinton acknowledges he was wrong now, and it was saying this is at the Mayo Clinic where they have the recognition, the pixel level recognition, but the radiologists are using it as an assistant and being able to do a lot more and spend their time doing more in-depth analysis. And it's a nice article on how humans and AI are working together rather than the AI merging in and saying, okay, we're going to do everything. AI going forward, how am I doing on time? Probably people are getting 8 minutes. Wow, that's cool. All right. So I played around a little bit, and I'm sure you've all done this, with chatbots just to see what they can do. And we all know about this hallucination problem. So here I asked it to generate an abstract for a scientific paper that describes the addiction of small panda bears to French fries and TikTok and how this is causing them to fall behind in their education. Okay, total nonsense, but I just wanted to see what it would do. Here's a gratuitous picture of red panda bears that it talks about. So I won't read the whole thing, but it's a very well-written, I'll maybe read one sentence here. Behavioral analysis revealed a strong correlation between increased consumption of French fries and time spent engaging with a simulated social media problem. Further research is warranted to fully elucidate the neurobiological underpinnings of this crispy scroll addiction. So, the point I'm making is we're all flooded by this stuff. So it's very easy to generate completely fake scientific articles, fake news articles, and it sounds plausible. The AI doesn't know if it's true or not. It just will happily produce billions of lines of this type of stuff. Here's maybe a slightly more serious example. So I gave it the following simple task. I said the neurosurgeon ate dinner and then blank went to sleep. what are the top 3 words blank could represent in this sentence, and what are the probabilities for each word. And I'm using Google Gemini here. I'm not picking on Google. They are funding me, but other chatbots will do similar things. And so it comes back with 3 words, and really disappointing. It's like the first word is he, 0.7, and the second word is not even she. It's immediately. And the third word is quietly, and it's like, really, 2025. So this is baked into the data. It's baked into the models, and companies are working hard, but it's really. It's in the essence of the models, and they have to kind of do workarounds to get it to not have these biases, in this case, a gender bias. I just flipped it around and had a nurse eating breakfast, and now it says she. It's like, okay, there's a lot of work we need to do here. And this is a hard problem. This is not an easy sort of fixed problem. It's not only things like gender bias, but all kinds of biases built in, because they're built on historical data, and that's all these models know. Here's one that I came up with a few years ago for another talk, and I thought the models would have fixed it by now, but they haven't. So I was born in July, which is true, and my sister was born in May, also true. Who is older? Well, I'm 5 years older than my sister, but so you really need to figure out what years we were born in to know the answer. But the chatbot models come back that May is before July, so therefore my sister is older. Okay, I went to OpenAI's public ChatGPT. It's also same answer. But even worse, I asked it how confident it is. I'm very confident, exclamation point, smiley face. May comes before July, your sister is definitely older. There's no ambiguity in that. I found this and I was like, I saw this yesterday or today, and I was like, okay, great. This exemplifies that these models just are overconfident, and we have to work really hard to address that. So how are researchers addressing such challenges? There's a lot of talk about bigger AI models, especially in places like Washington, D.C., scale, data centers, blah, blah, blah. Yeah, I mean, that certainly for some applications we need that. But I think, as researchers, academics need to think about other ways to get at this. Cleverer AI models, just rethink what we're doing. Do we just need brute force to do this? Safer, less biased, interpretable AI models, adding symbolic knowledge. There's work on neurosymbolic representations Rena Decker is doing, Alex Eiler and others, very interesting. Human AI collaboration, not that the AI is doing everything. So a little bit on some work I've been doing with Mark Stiver, a colleague here at UCI in cognitive science. We've had an NSF-funded project for a number of years now, lots of papers you can look at. And one of the things we do is we do user studies. So we put out, and I see some of the students here smiling because they're involved in this. We'll ask people to classify objects, in this case a bear, and we'll say, and here's the AI assistant. So we do various controlled studies. Merck's group is very good at this. And some of the images we make harder. So this one's slightly harder than the first one. And we've a lot of different questions we can ask here. Can the AI help the humans in decision making? Does AI confidence matter? Turns out it does. Are AI models well calibrated? Up to a point. And so lots of interesting work, lots of interesting new directions that this kind of work can go. One of the things in one of the papers, this is with Markel Kelly, a student that just graduated in my group who's on her way to eBay to help with safe and responsible AI there, also with Merck's group. There's a well-known result in cognitive science that problems that you think are difficult for you, that's the x-axis, you also think are going to be difficult for other people. That's, and we did this across math, geography, different types of problems. What we didn't expect was when we asked people about how hard would it be for an AI agent, they thought it would be much easier. The AI agent's going to be much better at all levels of difficulty. And we found this across different areas. If they found the AI is good at this, they think it's going to be good at everything else. So this has implications. The perception of AI as this all-knowing, very competent, better than other humans is one that, if we embed AI in some application, we need to be careful. People overtrust AI. Another paper that just came out about large language models was getting at the uncertainties. So let me try to explain left to right on the bottom here. We gave a language model different, fairly hard questions. The model, it's multiple choice, a little artificial. The model comes back with different probabilities. Here, there's 4 outcomes. It's pretty uncertain. Highest probability for C is 0.4 something. And we asked it to generate an explanation. And then we had people look at the explanations and say, how confident do you think the LLM is? And the text, even though the numbers in the model were fairly uncertain, the text was very confident. So there was, in going from the numerical representation to the text, people thought, in this case, that the model was 95% confident. And we saw this systematically over the whole experiment. And again, it's telling us that the language output is overconfident, but internally in the model, there's some hope that the model does understand that it doesn't know the answer, essentially. So the question is still, does AI know what it doesn't know? And at the moment, probably the answer is no. It tends not to know what its boundaries are. For example, if I ask you who is the finance minister in Ecuador, unless you're from Ecuador, I'm going to guess most of you will say, I have no clue. Let's say that straight away. But if you ask an AI, it'll go through reasoning steps and come up with a plausible answer and say, oh, I think this is the, blah, blah, blah. I think I'll skip over this in the interest of time. So what have we learned about AI in the past few years in research and business as well? Certain types of problems, like the related to software engineering, coding, it can be extremely good, really good. But it can also be very poor at simple things that we know how to do well. I didn't talk about robotics, but if you talk to robotics researchers, they'll tell you that in simulated worlds, robots are fantastic or very simple controlled environments, but you put them out into even a relatively safe room like this, and we're a long way from robots that can just work in the real world. There's just too many complexities. The AI systems are fallible, they make mistakes, they're difficult to test. Testing an AI system is really hard, and we don't understand them very well. We're treating them as big black boxes, and they can't explain their own behavior. I'll finish with a few comments about this question that I and other AI researchers get asked: is AI an existential threat to humanity? Now, I'm not going to be able to answer that. There's a lot of diversity among researchers about this. I'll give you my perspective on it. I usually answer yes, and not for the reason that robots are going to come in the door and take us over. There's a different reason, and let me explain. Here's the reason I don't think robots will take over for a while. This is a well-known video of a commercial robot and its failure modes, and so robots have a ways to go yet. Get past the robot. The reason I think there's a crisis is it's in education and learning, and it's real. And if any of you know teachers and talk to them, well, we're at a university, talk to our colleagues. We have AI-generated lecture slides, assignments, exams. We have AI-generated solutions by students, and increasingly AI comments and grading of papers and assignments. And is this where we want to go? I would ask ourselves. We're at a university. This is going to have massive implications, and we cannot blame the students. The students have the tools in front of them. They will do what's available. It's us, the adults in the room, to take responsibility here. There's been some very good articles recently. The Chronicle of Higher Education a few weeks ago, is AI enhancing education or replacing it? And it was very clearly interviewed a lot of people. It's not enhancing it. Let me see if I can read a little bit of this. Hang on a second. That wasn't supposed to happen. Wait a minute. Okay. ChatGPT creates no more benefit for their intellect than moving a barbell with a forklift does for their strength. We've been alert to this since late 2022, and students have consistently reported understanding that some uses of AI are harmful. Yet forgoing easy shortcuts has proven to be as difficult as following a workout routine, and for the same reason. The human mind is incredibly adept at rationalizing pleasurable but unhelpful behavior. This is well known in cognitive science. Gloria Merck, who's retired now, is in the informatics department, has written entire books on this. If we give students the tools, even the good students, they're going to be tempted. They're not going to do the hard work of learning. And I'll skip ahead to a sort of a larger scale problem. I think, for most of us in this room, when we grew up, we interacted directly with the world. We interacted with the physical world, with other people, with writing, whiteboards, chalkboards, with books, with original authors, and so forth. We now have introduced this intermediary, this AI, and it's very tempting, but students, in an English class, they're not going to read the text for the most part. They're just going to use an AI summary or generate an AI summary. And it's so prevalent that it's hard to blame them. So we're disconnecting ourselves. And especially if you've never had the experience of going through the original material, it's going to be very hard to really learn it. And what I would suggest we should be thinking about is the AI assistant, where the AI is available to help, but that's a much harder system to design, much less easy. It's much sort of cheaper and short-term to put just the AI black box in there, the ChatGPT, and the original works of Shakespeare are somewhere over there, and you get a summary. And it's, if you talk to teachers, if you read some of those articles I pointed to, it's a real problem. It's a huge problem. In fact, it's even worse. Rather than even the AI talking to us, we're headed towards having AI agents talk to each other. My AI agent at, my insurance company talks to the AI agent at your hospital, talks, and the human is like, what's going on here? And if you don't believe me, just on NPR yesterday, I heard that Meta is one of my favorite companies, is planning to replace human review of their new releases, new software, with AI. So AI is now reviewing other AI-generated software, and it's like, this just doesn't make sense. So there's a lot of irresponsible use of AI out there, and I'm glad to have the opportunity to, tell you what I think at least about it. And it's not just education. Scientific research is also under threat, serious threat. AI can today, right now, read and summarize prior work, generate hypotheses, run computational experiments at least, build predictive models, which we often don't understand, write papers, review papers. All of this is happening. The AAAI conference just announced it's going to have AI reviewing of papers. Yeah. Is this what we want for the future of science? We really need to think about it. And, papers are coming out now, I think they're real papers, I can't be sure, of documenting the level that this is happening. Okay, so AI today, extremely useful. I mean, fantastic achievements in various areas. But it's really important to know that we haven't solved the problems. There's still some fundamental problems. It's fallible, it's biased, it's overconfident, hard to understand and test, easy to overhype, it's undermining education, and of course, as we know, in the wrong hands, it can be very dangerous. So for researchers, and particularly those of you starting out, I would say look beyond the status quo. Remember that history. AI went in all sorts of different ways, and who knows what the future holds. Deep learning might not be the way to go on its own, at least. So AI is broader than deep learning. And you owe it to yourself to educate yourself more broadly about other aspects of AI. And think also not just about the technical aspects, but the societal implications. When all this stuff was in the lab and nobody was going to our conferences, it was fine. We could do our NSF-funded research and, it was nice. But now the stuff has been taken out to the real world, so we need to pay attention and make sure people are aware of the limitations. And for everybody else, for all of us, try to resist the hype. AI can do some amazing stuff, but it also has its blind spots. And like in technology, we shouldn't just be asking, can we do this with AI? But why are we doing this with AI? What is the long-term goal here? So sorry to end on a slightly negative note, but I think it's important, and I hope you enjoyed the talk. Thanks for listening.
We have time for exactly one question. Professor Vazirani.
How much should we believe that deep learning and neural networks is the canonical way to do AI? You sort of hinted that it may not be, but how would you?
Well, there are terms that, neural networks are universal function approximators and the limits. I think more from an engineering perspective, a lot of that is asymptotic as we get enough data, as the network is big enough. I think we're starting to see people think about, do we need a giant deep network to solve particular problems, or can we come up with clever, smaller functions that do what we need? So I'm sidestepping your question somewhat because it's somewhat philosophical. But I don't think deep learning as it currently stands is necessarily the answer. I think there will be some twists in the story going forward.
All right, let's give another round to Padhraic. He will be around to answer more questions. So at this point, I would like to invite Dr. Philip Herzig, the Chief Technology Officer for SAP, to present a medal associated with the inaugural chair to Professor Padhraic. Padhraic, come on. Philip?
Sure. All right, good afternoon. It's my pleasure to be here and also spend at least a few words on why we are together here and also present our perspective from the SAP side of the house. So first of all, it's a true pleasure to be here and celebrate this remarkable achievement here of Professor Padhraic Smyth. We are very excited about this, and also really not only do this celebration and this endowment of Hasso Plattner's professorship here, but also really deepen the partnership together with UCI. And you know, a few months ago, we announced this endowment here at the UCI in honor of Hasso Plattner, long-serving CEO, co-founder, and of course also longtime chair of the supervisory board. I actually had the chance to meet him just 3 weeks ago in his home in Germany. That's also why he's not here. He's currently in Germany. Usually he's here close to Newport Beach. Right now he's in Germany. And even though he is not officially associated with SAP anymore, he was just interested what we are doing with AI. So I had the privilege to be just 2 hours in his home. And we're doing not just COBOL, but it's actually maybe the sister or the brother, depending on how you want to view that. There's ABAP. Somebody knows ABAP? Most of the world's systems and finance and so on run on ABAP because that is what the SAP systems are still for the most part programming. And of course, we also need to transform them, right? There's a lot of legacy code out there. And I showed him like half an hour. We were sitting there together in his living room and doing code generation with AI on ABAP based on some of the large language models. It was super fascinating. But what was really astonishing to me, even though he's not associated with SAP anymore, this level of curiosity and the level of excitement still for new technologies and wanting to understand what is going on, right, with academia, of course, with UCI. He immediately asked what is going on here, what are we doing there, how do we work together with academia, how to make it better, how do we work, of course, also with his own institution, the Hasso Plattner Institute in Potsdam. So that level of curiosity and fidelity and really going deep, right, is really, even though he is, meanwhile, older than 80, right, I think 81 right now, there's just a level of excitement and curiosity that is just astonishing because he just wants to learn and really also coach people to get better. This deep passion is just phenomenal. And therefore, yeah, we are very excited and really also, again, proud to welcome Professor Padhraic Smyth, right, into the significant role. And this is important when Marx is not just an academic honor, right? It's a statement about the future that we want to build together. And again, just this lecture gave me the confidence that Padhraic Smyth is absolutely also the right selection for this overall, because what you just shared also in terms of the challenges, specifically in AI, that we are looking into to build a reliable but also responsible human-centered AI, that is really on us, right? And it's not, we truly also believe at SAP that the future is not just bigger and larger models, right, with more computation in the pure deep learning area, but a combination of multiple methods that require still simply more research. And this is why, beyond just this honor here today, we are really excited to work really closely here with UCI, with a lot of the professors, with the students here. And also this investment is not just for UCI, we also invest actually just down the road in Newport Beach, another team that looks into some of the challenges that we are aiming to solve for companies and our SAP customers around the world to really help them with AI to achieve more, but clearly in a reliable and responsible fashion. And therefore, we are really working and looking forward to really combine academia and the research world with relevant problems that we need to solve in the B2B world from an SAP standpoint. And therefore, we are very excited to look towards this collaboration. Thank you again for the partnership. We are very excited about this, so thank you very much. And we are looking forward to it. Thank you.
So in closing, thank you, Philip. In closing, a few thank yous. Let me once again thank everyone who made today's celebration possible. My sincere thanks and appreciation to our friends at SAP for their generosity and vision. I look forward to an exciting and productive partnership far into the future. My thanks to Professor Smyth for a fascinating lecture. Congratulations on his appointment as the inaugural chair. I look forward to his future accomplishments. AI is taking the world by storm, and research in academia in this field is more important than ever, so no pressure, Padhraic. My thanks to Bill Applied Innovation for hosting this event. Focus on entrepreneurship and technology transfer. This is the perfect venue for this celebration. Last but not least, my thanks to all of you, the community and friends of ICS for participating in this celebration. Please stick around, mingle during the reception, which is about to start.